Hey everyone and welcome. Today we're diving into one of the most important topics you'll ever face as a developer, especially in an interview: time and space complexity. You know, if you can nail this, you're not just showing you can write code, you're showing you can think like a real engineer.
So picture this. You're in that coding interview. You just solved a really tough problem. The code compiles, it runs, it gives the right answer. You're feeling pretty good about yourself. But then the interviewer leans forward and asks that one simple question.
Is your code any good? Because in that moment, just having code that works is really just the price of admission. The real interview starts now. It's about proving you understand the why behind your solution and how to make it better. And that's exactly what we're going to unpack right now.
So yeah, why isn't a working solution enough? Well, it's because the interviewer isn't just trying to see if you can get from point A to point B. They want to see if you can think like an engineer. And that always means talking about efficiency.
Now, you can't just say, oh, my code runs in 0.2 seconds. I mean, why not? Because that number is completely meaningless. It depends on the speed of your laptop, the programming language, what other tabs you have open. That's clock time, and it's useless for comparison. We need a universal yardstick, right? A way to measure an algorithm's efficiency that works on any machine anywhere. And that, my friends, is algorithmic time.
So, how do we actually build this universal speedometer for our code? If we can't use a stopwatch, what's the alternative?
Well, the answer is actually pretty straightforward. Instead of timing our code, we just count the number of basic operations it has to do. But here's the absolute key: we don't care about the exact number for a single run. What we really care about is the trend. As our input size, which we'll call n, gets bigger and bigger, how does that operation count grow? That's the billion-dollar question.
Okay, so to talk about this growth rate in a standardized way, computer scientists came up with this shared language. It's called Big O notation, and believe me, it's the language every interviewer expects you to be fluent in.
Now, if you crack open a textbook, you're going to see the formal definition, and it looks like this. It's super precise, very mathematical. But let's be real, it can look a little intimidating at first glance. So let's just cut through the math for a second. In plain English, all Big O is really asking is this: as the input to your function gets massive, how does the amount of work change? Does it pretty much stay the same? Does it grow at the same pace as the input, or does it just completely explode? That's all we're trying to describe here. To make this even easier, you can think of all the common Big O types as rungs on a ladder. The best, most efficient ones are at the top, and as you go down, things get a lot slower.
Okay, let's walk down this ladder, because this is what it all comes down to in an interview. At the top, you have O of 1, or constant time. This is the holy grail. Your code takes the same amount of time no matter how big the input is. O of log n is also amazing. Think about finding a word in a perfectly balanced dictionary. Then you have O of n and O of n log n. These are your bread and butter, good, solid, acceptable solutions for a lot of problems. But once you hit O n squared, or quadratic time, that's a yellow flag. It might be okay for a first try, but a good interviewer is going to push you to do better. And if you end up with a cubic or, heaven forbid, an exponential solution, that's a huge red flag. It's time to go back to the drawing board.
So how do we actually find the Big O for a piece of code? Let's take the simplest possible example, a single for loop. What's the code doing? It's just looping from 0 up to n. The key operation, the real workhorse, is that count plus plus inside. So, how many times does it run? Well, it runs once for each item in the input. If the input size is n, it runs n times. The work grows in a straight line with the input. Simple as that. The complexity is O of n.
All right, so far we've been all about time. But any experienced engineer will tell you that time is only half the story. There's another critical resource we have to think about, and that's memory.
So just to recap, we've nailed down time complexity, right? It's all about how the number of operations scales up as the input size grows.
But an interviewer isn't just going to care how fast it is. They're also going to ask, okay, but how much memory does this thing eat up?
And that right there is space complexity. It's literally the same question. We're just swapping out time for memory. As your input n gets bigger, how much more RAM does your algorithm need? For instance, if you create a new array and copy all the input into it, well, the memory you need grows directly with the input size. Boom, that's ON space complexity. It's the other side of the efficiency coin.
Okay, now we get to the really fun part. This is where you go from just knowing the definitions to actually thinking like a pro. Because the best solution, it's not always the one with the fastest time complexity. It's all about understanding the trade-offs.
Check out this classic scenario.
Al has a theoretically fast algorithm. It's O of n log n. Bob has a theoretically slower one, O of n squared. So Al should always win, right? Well, they run a test, and for any input with less than 100 items, Bob's slower algorithm is actually faster. How is that even possible? It's because Big O cares about what happens when n approaches infinity. It ignores all the small, constant setup costs that can make a simpler algorithm way faster for small jobs.
And that brings us to the most important takeaway of all. A truly great engineer doesn't just state the big O. They talk about the trade-offs. They'll say something like, okay, my solution is O of n time, but it also uses O of n extra space. Now, if memory is super tight on this system, we could use an O of n squared approach that only needs constant space. That discussion, that is what absolutely aces a coding interview.
And that leaves us with one final thought to chew on. We've talked about how to analyze code that's already written. But the real next level, the real mastery, is when you can use this as a design tool. Can you look at a problem, visualize 2 or 3 different ways to solve it, and analyze their time and space trade-offs in your head before you even type a single line of code? When you can do that, you're not just solving problems anymore, you're architecting solutions.